What is fusible resistors and characteristics and uses of fusible resistors? Fusible resistors, also known as fuse resistors or safety resistors, are a type of electronic component designed to protect circuits from excessive current or overloads. They combine the functions of a resistor and a fuse in a single package. Fusible resistors are typically used in applications where circuit protection is critical, such as in power supplies, automotive electronics, and industrial control systems. Here are some key characteristics and uses of fusible resistors. Resistance value, often referred to simply as resistance, is a fundamental electrical property of a resistor. It quantifies the opposition that a resistor offers to the flow of electric current through it. Resistance is measured in ohms, symbol omega, and is a crucial parameter in electronic circuits. Here are some key points about resistance value. Unit of measurement. The unit of measurement for resistance is the ohm symbol, named after the German physicist George Simon Ohm. 1 ohm is defined as the amount of resistance that allows 1 ampere of current to flow through a conductor when a voltage of 1 volt V is applied across it. Mathematically, this is expressed as Ohm's law, V equals I asterisk R, where V represents voltage, I represents current, and R represents resistance. Symbol. In circuit diagrams and equations, resistance is represented by the symbol R. Resistance value range. Resistors come in a wide range of resistance values, from fractions of an ohm, milliohms, to millions of ohms, megohms. The specific resistance value of a resistor is determined by its construction and materials. Tolerance. Resistors typically have a tolerance rating that indicates the allowable deviation from their nominal resistance value. Common tolerance values for resistors include 1%, 5%, and 10%. For example, a resistor with a nominal value of 100 ohms and a 5% tolerance may have an actual resistance between 95 ohms and 105 ohms. Color coding. Many resistors, especially through-hole resistors, are color-coded to indicate their resistance value and tolerance. This color code uses a series of colored bands or stripes to represent the numerical value and tolerance of the resistor. Engineers and technicians can decode these colors to determine the resistance value. Role in circuits. Resistors are used in electronic circuits for various purposes, such as voltage division, current limiting, signal attenuation, and biasing. They help control the flow of current and voltage levels in a circuit, ensuring that electronic components operate within their specified ranges. Ohmic behavior. Ideally, resistors exhibit ohmic behavior, meaning that their resistance remains constant regardless of the voltage applied, within their specified power rating, and that they obey Ohm's law. In practice, real-world resistors may have some deviations from ideal behavior, especially at high frequencies or under extreme conditions. Choosing the right resistor with the appropriate resistance value is essential in designing electronic circuits, as it directly affects circuit performance, current flow, and voltage levels. The correct selection ensures that the circuit functions as intended and that components are protected from excessive current. The fuse function is a critical aspect of electrical and electronic circuits designed to protect equipment, components, and wiring from excessive current and overloads. Fuses are safety devices that are specifically engineered to break the circuit when certain conditions are met, thereby preventing damage to the connected devices and reducing the risk of fire or other safety hazards. Here's how the fuse function works. Overcurrent protection. The primary purpose of a fuse is to protect against overcurrent conditions. Overcurrent can result from various factors, including short circuits, component failures, or excessive loads. When the current in a circuit exceeds the rated current of the fuse, it is considered an overcurrent condition. Heat-based operation. Fuses are designed with a conductive element, typically a thin wire or strip, made of materials with known electrical and thermal properties. The conductive element has a specific current carrying capacity. When the current passing through the fuse exceeds this capacity, it generates heat in the conductor. Melting or opening. As the heat builds up in the conductive element, it eventually reaches a critical temperature. At this point, the fuse's design is such that the conductive element melts or opens, creating an air gap in the circuit. This deliberate interruption of the circuit disconnects the power source from the load, effectively cutting off the current flow. Protection mechanism: the melting or opening of the fuse prevents excessive current from reaching downstream components, which could otherwise be damaged or compromised. It also helps prevent overheating of wires and the risk of electrical fires. Irreversible action: fuses are generally designed for one-time use. Once a fuse has operated and opened the circuit, it must be replaced with a new one to restore electrical continuity. This ensures that the protective function remains intact. Rating and sizing: fuses come in various sizes and ratings, and it's crucial to select the right fuse for a specific application. The fuse's rating is determined by its current carrying capacity, typically measured in amperes, A, and its voltage rating. The voltage rating indicates the maximum voltage at which the fuse can operate safely. Types of fuses: there are various types of fuses, including fast-acting fuses, slow-blow fuses, and miniature fuses, each with specific characteristics suited to different applications. For example, fast-acting fuses respond quickly to overcurrents, while slow-blow fuses tolerate brief current surges. Fuses are widely used in electrical and electronic systems, including home electrical circuits, industrial machinery, automotive systems, and electronic devices. They play a vital role in preventing electrical faults, equipment damage, and electrical fires by interrupting the circuit when necessary to protect against excessive current. Voltage rating, also known as voltage class or voltage category, is a critical specification for electrical and electronic components, especially those designed to be used in power distribution systems and circuits. It indicates the maximum voltage that a component can safely handle or operate it without risk of breakdown, insulation failure, or other electrical issues. Here are some key points about voltage rating. Definition: voltage rating specifies the highest voltage level that a component is designed to withstand continuously or for a specified period without experiencing electrical breakdown or damage. Unit of measurement: voltage ratings are typically expressed in volts, V. The voltage rating indicates the voltage level in the circuit at which the component will maintain its electrical and mechanical integrity. Safety and reliability: components with the appropriate voltage rating are essential for ensuring the safety and reliability of an electrical or electronic system. Using components with insufficient voltage ratings can lead to catastrophic failures, fires, or electrical hazards. Different components, different ratings. Different types of electrical and electronic components have varying voltage ratings based on their intended applications and construction materials. For example, circuit breakers, transformers, capacitors, and resistors will have distinct voltage ratings. Insulation and dielectric strength: in many cases, voltage rating is related to the insulation or dielectric strength of the component. For instance, high-voltage cables and insulators are designed with materials that have high dielectric strength to prevent electrical breakdown. Overvoltage protection: in some applications, components with higher voltage ratings may be selected to provide an extra margin of safety in case of voltage spikes or transient overvoltages. This helps protect the component from damage during such events. Matching components: it's crucial to ensure that all components within an electrical or electronic circuit have voltage ratings compatible with the system's voltage levels. Mismatched voltage ratings can result in system malfunctions or failures. Markings: electrical and electronic components often have their voltage ratings clearly marked on their housings or data sheets. Engineers and technicians should consult these markings and specifications to ensure that the components are suitable for the intended application. Testing and certification: components used in safety-critical applications or specific industries, e.g., aerospace or medical devices, may need to meet specific standards and undergo testing and certification to verify their compliance with voltage ratings and safety requirements. In summary, voltage rating is a crucial specification for electrical and electronic components, and it plays a significant role in ensuring the safe and reliable operation of electrical systems. Selecting components with the correct voltage rating is essential to prevent electrical breakdown and potential hazards. The power rating of an electrical or electronic component is a crucial specification that indicates the maximum amount of electrical power it can safely handle or dissipate without overheating or becoming damaged. Power rating is an essential consideration when selecting components for electrical circuits and systems. Here are some key points about power rating. Definition: the power rating of a component, usually expressed in watts, W, represents the maximum power, energy per unit time, the component can handle or dissipate under specified operating conditions without exceeding its temperature limits or other critical parameters. Importance: power rating is critical for component selection and usage because exceeding the specified power rating can lead to overheating, component failure, and potentially hazardous conditions in the circuit. Components with power ratings: various electrical and electronic components have power ratings, including resistors, capacitors, inductors, transistors, diodes, transformers, and more. Each component type may have different factors affecting its power rating. Resistors: the power rating of a resistor indicates the maximum amount of heat it can dissipate without damage. Exceeding the power rating may cause the resistor to overheat and change its resistance value. Semiconductor devices: components like transistors and diodes have power ratings that specify the maximum amount of power they can handle while maintaining their electrical characteristics. Exceeding this rating can lead to semiconductor device failure. Transformers: power transformers are rated based on their capacity to handle both voltage and current without saturating or overheating. Transformer power ratings are commonly expressed in volt-amperes, VA. Capacitors and inductors: these passive components may have power ratings that relate to their ability to handle voltage and current without breaking down or undergoing excessive heating. Voltage and current considerations: when calculating power in a circuit, it's essential to consider both voltage and current. The formula for calculating electrical power is P, power, equals V, voltage, asterisk I, current. Knowing the power rating of components helps ensure that the product of voltage and current does not exceed the rated power. Derating: in some applications, components may need to be derated, which means they are operated below their maximum rated power to ensure long-term reliability and safety. Derating is common in critical or high reliability systems. Operating conditions: the power rating of a component is typically specified for specific operating conditions, including ambient temperature. Deviating from these conditions can affect the component's ability to handle power. Data sheets: manufacturers provide power rating information in component data sheets, along with guidelines for usage and derating where applicable. Engineers and technicians should consult data sheets when selecting components. In summary, the power rating of an electrical or electronic component is a fundamental specification that guides the proper selection and usage of components in circuits and systems. Adhering to these ratings is crucial to ensure reliable and safe operation while preventing component overheating and damage. Resistance tolerance is a specification associated with resistors and indicates the allowable deviation from the specified or nominal resistance value of the resistor. It quantifies how closely the actual resistance of the resistor can be expected to match its marked or rated resistance value. Resistance tolerance is expressed as a percentage and is an essential parameter to consider when selecting resistors for electronic circuits. Here are the key points about resistance tolerance. Definition: resistance tolerance represents the range within which the actual resistance of a resistor is expected to fall relative to its nominal, marked or rated, resistance value. It is usually expressed as a percentage of the nominal resistance. Tolerance values: common tolerance values for resistors include 1%, 2%, 5%, 10%, and 20%. The lower the tolerance value, the more tightly the resistor's actual resistance is expected to match its rated value. Example: suppose you have a resistor with a nominal resistance of 100 ohms and a 5% tolerance. This means that the actual resistance of the resistor can be anywhere between 95 ohms, 100 ohms, 5%, and 105 ohms, 100 ohms plus 5%, and still be within spec. Color coding: through-hole resistors, such as carbon film or metal film resistors, often use a color-coded system of bands to represent the resistance value and tolerance. The tolerance band on the resistor is typically a different color from the bands representing the resistance value. Precision and accuracy. The choice of resistance tolerance depends on the precision and accuracy requirements of the circuit. In applications where precise resistance values are critical, lower tolerance resistors, e.g., 1% or 0.1%, are used. In less critical applications, higher tolerance resistors, e.g., 5% or 10%, may be acceptable. Effects on circuit performance. The tolerance of a resistor can affect the overall performance of a circuit. For example, in voltage divider circuits or applications where precise gain control is required, lower tolerance resistors are preferable to ensure accurate results. Cost consideration. Lower tolerance resistors are generally more precise but also more expensive to manufacture. Therefore, component cost may be a factor in selecting the appropriate tolerance. Matching resistors. In some applications, it is essential to use resistors with the same or very close tolerance values to ensure balanced circuit operation. This is common in circuits like operational amplifier, op-amp, precision amplifiers and Wheatstone bridge configurations. Test equipment calibration. In calibration and measurement applications, resistors with tight tolerance values are often used to maintain the accuracy of test equipment. Tolerance stacking. In circuits with multiple resistors in series or parallel, the tolerances of individual resistors can combine or stack to affect the overall resistance of the network. This should be considered during circuit design. In summary, resistance tolerance is a critical parameter when selecting resistors for electronic circuits. Engineers and designers should carefully choose the appropriate tolerance value based on the specific requirements of their application to ensure the desired level of precision and accuracy in their circuits. Fusible resistors have several applications in electronics and electrical systems where circuit protection and safety are paramount. Here are some common applications of fusible resistors. Power supplies. Fusible resistors are often used in power supply circuits to provide overcurrent protection. They can help prevent damage to sensitive components and equipment in case of a fault, such as a short circuit or overload. Motor control circuits. In motor control applications, fusible resistors can be used to protect motors and motor drivers from overcurrent conditions. This helps extend the lifespan of the motor and ensures safe operation. Automotive electronics. Fusible resistors are used in automotive systems to protect various components and circuits, such as those in the engine control unit, ECU, airbag systems, and power distribution networks. They help prevent electrical fires and damage to critical components in the event of a fault. Industrial equipment. In industrial automation and control systems, fusible resistors provide protection for equipment and control circuits. They are commonly used in PLCs, programmable logic controllers, and other industrial control devices. Telecommunications. Fusible resistors are used in telecom equipment to safeguard against overcurrent conditions that could damage sensitive electronics, including routers, switches, and communication infrastructure. Medical devices. Medical equipment often incorporates fusible resistors to ensure the safety and reliability of critical functions. They protect against overcurrent events that could compromise patient care. Consumer electronics. Some consumer electronics devices, particularly those with power supply or charging circuits, may include fusible resistors to enhance safety and prevent damage to the device or charger in case of electrical faults. Lighting systems. Fusible resistors can be used in lighting control systems and fixtures to protect against excessive current, helping to maintain the integrity of the lighting system. Battery protection. In battery management systems for rechargeable batteries, e.g., lithium-ion batteries, fusible resistors are used to protect against overcurrent and short-circuit conditions that could lead to battery damage or safety hazards. Test and measurement equipment. Fusible resistors can be incorporated into test and measurement equipment to protect sensitive measurement circuits from voltage or current surges during testing. Inrush current limiting. Fusible resistors can serve as inrush current limiters when used in series with other components during power-up to reduce the initial surge of current that can stress components like capacitors and power supplies. Overload protection. In general, fusible resistors are used wherever overload protection is required to prevent equipment damage, fires, and safety hazards caused by excessive current flow. The specific application of fusible resistors depends on the requirements of the system or device they are integrated into. Their role is to act as a safety mechanism that disconnects the circuit when overcurrent conditions are detected, thus protecting sensitive components, preventing damage, and ensuring the safety of both equipment and users. Color coding is a method used to represent information or values through the use of colors. In the context of electronics, color coding is commonly used for various components, wiring, and resistors to convey information such as component values, tolerance, or polarity. Here are some common applications of color coding in electronics. Resistor color coding. Color bands on resistors are used to indicate their resistance value and tolerance. The color code consists of several bands, each representing a different digit or multiplier. For example, a resistor with color bands of brown, black, and red represents a resistance value of 10,000 ohms or 10 kiloohms with a tolerance of 2%. Capacitor color coding. In some capacitors, color coding is used to denote capacitance values. However, this is less common than other methods such as numeric markings or alphanumeric codes. Inductor color coding. Some inductors use color coding to indicate their inductance value, but like capacitors, it's less common than other methods. Component polarity. In electronic components like diodes and electrolytic capacitors, color coding is sometimes used to indicate polarity. For example, a stripe or band on a diode can denote the cathode side, while the anode side is typically unmarked. Wiring and cable identification. In electrical and electronic systems, color coding is used to identify wires and cables, especially in power distribution, telecommunications, and networking. Different colors may signify different functions or voltages. Terminal identification. In some connectors and terminal blocks, color coding is used to designate specific terminals for ease of connection. For instance, in audio connectors, the color coding of terminals helps users correctly connect speakers. Component markings. In addition to color bands, some components may have alphanumeric markings printed on them in different colors to indicate values, ratings, or part numbers. Safety and warning labels. Color coding is used for safety labels and warning signs in electronics, especially in areas where specific safety precautions are required, such as high-voltage equipment or hazardous environments. PCB, printed circuit board, traces. On PCBs, colored lines or markings may be used to indicate specific signal paths or to distinguish different functional sections of the board. LEDs, light-emitting diodes. The color of an LED is a crucial indicator of its characteristics. Different colors represent different wavelengths and light output. For example, red LEDs emit red light, while blue LEDs emit blue light. Component identification. Color coding is sometimes used for quick visual identification of components, especially in educational settings or for beginners. For example, certain types of transistors may have colored cases to signify their characteristics. It's important to note that while color coding can be a helpful visual aid in electronics, it should never be the sole method of identifying component values or characteristics. Components should always be verified using datasheets, part numbers, or other reliable methods to ensure accuracy and prevent errors. Additionally, color coding conventions may vary between manufacturers, so it's essential to consult documentation when working with specific components or systems. It's important to choose the appropriate fusible resistor based on the specific requirements of your circuit, taking into account factors such as resistance value, power rating, and voltage rating. When a fusible resistor blows or opens due to overcurrent, it typically needs to be replaced with a new one to restore circuit functionality and protection.